This is the third lecture of modern physics, and as I promised in the last class that I'm going to record this for whoever is not able to be present during our offline lecture. But seems like nobody is going to be around because of the college week, and that's okay. But I decided not to skip the lecture because we don't have much time this semester. Another thing I promised is that I am going to introduce quantum mechanics, and you probably already heard a lot about how weird, how strange quantum mechanics is, and therefore I'm going to introduce quantum mechanics with its strangest features. Therefore, I'm not going to, pretend that quantum mechanics is perfectly okay, perfectly intuitive, and we just go along with it. I'm really going to start it with all of its weirdness, strangeness, so that you know what we're going to be working with. And this lecture is really not my lecture. This entire lecture is actually based on a famous lecture by one of the most famous physicists, Richard Feynman, because I think nobody can teach quantum mechanics. I mean, I haven't come across anything better than this lecture that he gave. So I'm just going to present his lecture, his introduction to quantum mechanics, the best possible way I can. So let's start. Okay. We are going to talk about the electrons, particles, and you have heard about the wave particle duality. You have heard about this a lot. Like particles behave like waves, waves behave like particles in your maybe chemistry class or during the higher secondary or something. So what it really is, what do we mean by this, that's what we're going to begin with. And this is where the heart of quantum mechanics really lies. So wave-particle duality. We're going to start with a particle. We thought it's a particle called the electron. Okay. We had a classical understanding that it's a particle. We have been treating this as a particle. What do we mean by particle? We mean like bullets, gun bullets, marbles, things like that. Those are kind of what we mean by particles. Waves on strings, like strings vibrate like this or like this, or waves on a pond, So when we have a pond of water and you drop a stone, what do you see? A wave progressing like this. That's a wave. Or you also know electromagnetic waves, or maybe just simply traveling wiggles, Well, this is pretty much like the water waves, or sound waves, where the pressure in the medium keeps changing. Like here, the air is denser and then less So I mean, it's hard to really draw a pressure wave like the sound wave. It's the if we plot the pressure, so the pressure, and this is the space over which it's traveling, then higher pressure, then lower pressure, higher pressure, lower pressure, higher pressure, lower pressure. This is a pressure wave where the air gets compressed in one part and then, you know, the opposite of compression. So the expansion of air and then compression, then expansion, then compression. This is pressure wave. So all sorts of waves and particles like bullets, like stones, dust, whatever, those are our classical understanding of particles. What is the duality? Well, to understand duality, we're going to start with what we know distinctly, or definitely, that this is particle behavior. And then waves, this is what we mean by waves in classical physics, that we are absolutely sure. So let's first start with definite particles. So particles. Let's draw. Let's use a different color. Blue. Particles. Let's introduce particles and define what we mean by particles through an experiment. An experiment with bullets. Okay, an experiment with bullets. So what we have is a gun, okay, a gun, but not really, it's not a perfect gun. So what it does, it sprays bullets in all directions, like in a really large angle, really large angle. It shoots bullets, not in one direction, but in all possible direction within a large angle, randomly, like sometimes in this direction, then sometimes here. There is no pattern, it's just random, okay, in all directions. And the energies of the bullets are fixed. So they have the same speed, but just randomly in all possible directions within this angle, it's coming out. Sometimes in this direction, sometimes in this, like that. Other properties. So random direction, roughly same kinetic energy of the bullets. Bullets are indestructible. You cannot break them. They're always in one lump that doesn't break, and they also do not merge. So each bullet, even if they hit each other or hit a wall or anything, they remain intact. And the rate of shooting of the bullets is so low that at a time one bullet is coming out. It's not like, so low rate of shooting, okay? So not like two bullets coming out together. It's always one bullet at a time, okay? And then another bullet after some time. Randomly, of course. If this one comes out in this direction, the other one might come out in this direction or any direction. It's just absolutely random. But very low, okay? Rate, very, very low rate. All right, so these are the features of this gun and the bullets. Now, the gun is here, bullets are coming out like this. Then you have a wall in front of it. the wall has two small holes. Only one bullet can pass through it. Okay, so you have one hole here. Let's call it number 1. Another hole here. Let's call it hole number 2. Okay, we have 2 holes. And we have another wall after a certain distance. This is a solid wall without any holes. Another wall. So what happens is sometimes one of the bullet crosses this hole, passes through this hole, and just hits the wall somewhere. Now, it might hit the edge of the hole and might reflect back in this direction or like this. So it can go anywhere randomly on the wall. We don't have any control over where it can go, right? Similarly, with the other hole, it could just, one of the bullet just might, come exactly along this hole. It might pass through it, or it might bounce back and go in that direction, or in this direction, like that. Now, if you really kept a detector here, detector is just a box that can collect the bullet coming in its direction, and it has sand inside it so that it can stop the bullet in its intact shape. Then if we keep this detector in some position, so let's say directly opposite to the gun, it's x equal to 0, and then we have the detector placed at x, okay, x distance away from 0. So this is our positive x direction, this is our negative x direction, this is our x direction. And this detector can move freely on this wall and collect bullets. Now, if we keep this detector at certain position x, and bullets are coming out randomly but at low rate in all possible directions, so obviously some of the bullets enter these detectors, others just hit the walls. So for a certain period of time, let's say for delta t or whatever, 1 hour, 1 minute, for whatever period, a fixed period of time, if you count how many bullets have entered this detector divided by how many bullets hit the wall. So basically, let's say number of bullets that entered the detector in that particular time delta t is nd, and in that exact period of time there are n total number of bullets that hit the wall. Then if we divide nd by nw, we actually get the probability of a bullet reaching the position x in the wall. This is pretty straightforward, right? That will be our probability. Now, here is the thing. Of course, the rate is very low, which means at a time when a bullet reaches the wall, it either passed through hole number 1 or through hole number 2, right? It's a bullet. So it either went through this hole or that hole, because at a time just one bullet is coming. There are no 2 bullets coming together. So one bullet, when it hits the wall or hits the detector, it actually passes through one of the hole and then going and reaching the detector. After some time, the next bullet is coming. That might be going through hole number 2 and coming there. But we are not talking about that. We are saying that it definitely came through one of the holes while reaching to the detector. So, if we now, let's say, if we block this hole with something, if we block this hole and just kept this hole number 1 opened, then obviously these bullets are only due to the bullets, these hits are only due to the bullets coming through hole number 1. So then what we get when we divide the number of bullets inside the detector divided by total number of bullets hitting the wall in a particular time, that's what we call the P1. The probability of a bullet reaching the detector at position X, at distance X from the origin. Okay? Let's call it P1 of X. I mean, detector could be here and then it could be here. For different position of X, we calculate this probability. So let's say for 1 minute, we put it at X1 and then we get some number of bullets and then some hits on the wall. That ratio for one minute we calculate. Then in another position, X2, we repeat this. And this way, for all possible X's, we get these probabilities. So it's a distribution. It's a distribution. How will it look like? Well, if you plot it, let's use a different color for plotting. So this is our x-axis. This is our origin. This is our x direction. Well, it intuitively, it's a bullet, and we are going to find a peak around directly on the opposite side of the hole here, and then less number of bullets on this side, less number of bullets on the other side. If you do the experiment, you will see this will be the distribution of the bullets, or the probability of finding a bullet in a position X. That will be the distribution. If you repeated this experiment by closing hole number 1 and kept hole number 2 open, then we are going to get a similar distribution, but this time the peak will be around the position exactly opposite to the hole number 2. So this distribution was P1. Now we will get another distribution for hole number 2. When the hole number 1 is closed, we'll get a distribution like this. And let's call that P2 with hole 1 closed. Okay, hole 2 open is P2. Now, if I say, so obviously one does not depend on the other, and obviously if I now say that we open both holes, so bullets are coming out through any of the holes. So if we ask, like, what is the probability distribution of a bullet hitting the detector at position X? If both the holes are open, then it's a question of, so it is obviously that the probability is for the bullet coming out in either one hole, through either hole number 1 or through hole number 2. The bullet came either through hole number 1 or it came through the hole number 2. And that's, these two events are independent, right? And we expect just the sum of the probabilities. And in fact, if you do the experiment, you will, keeping the both hole open, you will see that the probability will look like this, which is, let's call that P1. So the P12 is the probability of finding a bullet in a position X when both the holes are open. So it's the probability that the bullet came through any of the holes and reached the position X. And this shape is understandable. This is simply P12 equal to P1 plus P2. While P1 is just the probability of the bullet of reaching X when only the hole 1 is open, and P2 is only when the only hole open is 2, and P12 is when both holes are open. Nice. This is what we call a particle behavior. There is no interference when the two holes are open. One bullet is not affecting the other. I mean, if the rate was really high, many bullets coming out together, it was possible that one bullet, while going in that direction, the other bullet coming in this direction, hit each other, and then they, redistribute. That would be a sort of interference. But we are saying that the bullet shooting rate is so low that at a time, really, only one bullet is coming and it's passing through the hole. The other bullet is coming sometime after the first bullet. So there is no interference, and this is absolutely what we mean by particle behavior. Okay, let's now proceed to our next classical object called the waves. Okay. So, in particles, each probability is independent. One does not affect the other, and we say there is no interference. Now we are going to study another classical object called a wave, waves. And let's do a new experiment, an experiment with water waves or ripples, water waves. Okay. An experiment with water waves. This time we imagine, or we do the experiment with a water surface, a pond. Imagine you are looking at a pond or a lake or a pool, swimming pool, which is absolutely calm. There is no, indoor, let's say, no air, no wind, nothing. So perfectly still water. But then you put a wall here. Okay. The wall has 2 holes again. Then you start creating waves here by doing a motion with something, or dropping a stone, or just oscillating something up and down. What it does, it creates circular waves emanating from this disturbance. They're traveling like this. And we know from diffraction of waves that these holes will act like new sources of waves. So from these holes, new waves will start generating and traveling like this. From that hole, let's draw that with another color. That hole will also act like another source of waves, like this. And they will travel like this. Now, instead of putting a wall, let's put a beach kind of situation here with sand, because otherwise there is a problem that if it's a solid wall, the waves are going to hit the wall and then reflection will start from the wall. Those reflected waves will start traveling back, and then it will be a messy situation with standing waves and all those things. We want an absorber that the waves just end there, just gets absorbed, nothing coming back from that direction. Okay, so some sand maybe here. But we have a detector that measures the height of the wave or the intensity, how high the amplitude of a wave is. So that's the detector. And once again, at the center position we have x equal to 0, and in this direction at a distance we have the detector. At a distance x we have the detector that can detect the intensity, detect a wave and measure its intensity. What is the intensity at that position? Now, once again, just try closing this one hole, okay? Let's close one of the holes. So once again, let's call it hole number 1, and this is hole number 2. If we close the hole number 2, then what we are going to see is just simple waves spreading like this. And it will have highest amplitude here, exactly opposite to the hole. And so if we plotted, let's plot in red. If we plotted the intensity, okay? If we plotted the intensity when only one hole number 1 is open, we will see something like this. I1. It will be highest exactly at the opposite side of the hole, here. And then diminishing on both sides. If we did this experiment and that's I1, intensity. Now if we close hole number 1 and keep the hole number 2 open, then similar thing will happen. Circular waves will start coming out from this hole, and the detector will get maximum intensity exactly the position exactly opposite to hole number 2. Let's call that I2, the intensity distribution of waves coming out of hole number 2 when hole number 1 is closed. Okay. What happens when we open both the holes? Any guesses? What will happen? Well, just like the individual cases, of course, waves will be coming out like this and reaching the wall or the detector. Now, what will be the intensity plot? How will the intensity plot look like if we kept both the holes open? will it be a sum of, just like the bullets, I1 plus I2? Will it look like this? Or something else? You know the answer. You definitely know the answer. And that's no. It doesn't look like that. When both holes are open, something strange happens. The plot, actually the distribution of intensity, looks like this. Now what is that? That we know. Well, that is the intensity I12. That is the intensity distribution of the waves detected by the detector when both the holes are open. And we know that this is absolutely not I1 plus I2. I12 is not equal to I1 plus I2. It does not, so the waves do not behave like bullets. That's what we call a wave nature. This is called the wave nature. That means clearly there is some interference term, interference. There is some interference between the two waves. And that's why the I12 looks like this. That is pure wave behavior. Now the final part, we're going to look at electrons. How do they behave? Do we see bullet-like behavior? That is, when we keep both the holes open, do we see just individual probabilities summing up P1 to equal to P1 plus P2? Or do we see a wave-like behavior? P1 to equal to P1 plus P2 plus some interference between P1 and P2. Or something entirely else, something new that we have never seen before. Well, let's find out. Let's do another experiment. This time with electrons. An experiment with electrons. This time, let's put an electron gun here. An electron gun. Not going to the details of the gun. Just the part that we're interested in this particular case. That it shoots electrons, just like bullets, in all possible directions within a big angle. Within this big angle, it shoots electron in all possible directions. Random shooting of electrons. 2. They're almost mono-energetic, meaning kinetic energies of all these electrons are similar. Like all the electrons coming out will have almost the same kinetic energy. Third, electrons are indestructible. They do not get broken up. They're always in one piece when we detect them. Or like anywhere. They exist in one piece. You cannot break an electron. Okay? That's an assumption we're making. Third, anything? Oh, the low rate of shooting. Low shooting rate. Once again, no two electrons are coming out from the gun together. There is always one electron coming out. One electron passing through a hole and going to the wall or the detector. Then another electron after some time. Okay? But randomly, I mean. So when you see the hit in a wall, you'll see click, 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 click. But not two electrons at the same time. Randomly. Uniformly, but randomly. And in all possible directions, they're coming out inside a large angle. So these are the assumptions that we are making before starting this experiment. Or we're choosing the gun like that. Okay. Now, once again, we have a wall with two holes, closely punched holes on a wall. Hole number 1, hole number 2. And then we have another wall, an absorber that just captures the electron, doesn't reflect it back, doesn't let it pass through, it just stops the electron. Once again, we have a detector that can capture an electron, and let's say it's connected to a loudspeaker. So when it gets hit by an electron, there's a sound, click, okay? And we can count that hit. So click, 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 click. So there are 4 clicks. So we can just count the hits and we know how many electrons have entered the detector in a certain period of time. But once again, it's like a bullet case. We can hear these clicks clearly and we know that these are like bullets. There are clicks. So once again, we can define probability of number of electrons that hit the detector divided by total number of electrons that hit the wall. That's the in a certain amount of time, and that's the probability. So once again, the center is x equal to 0 and the detector is at a position x. If we kept the detector in a position x, then and for a certain amount of time we counted the number of electrons captured by the detector and divided this by the number of electrons that hit the wall within that period of time, then that will be our probability of an electron reaching the position x. If you did this experiment by putting this detector in all possible positions, then you get a probability distribution. which is a function of x. Okay, p of x, something like that. Now, if we kept one of the holes closed, so let's say we kept the hole number 2 closed, then of course all the electrons are only passing through hole number 1 and reaching various position, and we call that the probability P1 of x. The probability of detecting an electron at a position x that came through hole number 1. Similarly, we could close hole number 1, keeping hole number 2 open, and that will be our probability P2x. And if you did this experiment, you will see that they look like this, just like the bullets. Opposite to hole number 1, there will be a peak of P1. So P1 of x is in this direction. P1 of x, this is the probability distribution when hole number 2 is closed. And then you close hole number 1 and you get the other probability distribution, P2 of x. Once again, the question is, what happens when we open both holes? What are we going to see? Are we going to see, just like the bullets, P1 plus P2, a P12, a probability when both holes were opened, P12? Is it just P1 plus P2, like the bullets, or something else? Well, interestingly, turns out it looks like this. Now that's crazy. That is our P12 of x. Probability of a bullet. Probability of finding a bullet at a position x, that when both the holes were opened. Now, the thing is, our proposition is that it's not a bullet, electron. Okay, electron. So our proposition is that the electron, of course, came through one of the holes. Why? Because, well, at a time, first of all, at a time one electron is coming out. Secondly, we detect only one click. It's not like the electron came and split up and went through both holes, interfere with each other, and then we would hear two clicks, click, click. Or click, like two hit very closely. But what we hear is just one click, click, then click, then click, click, but separate clicks, okay? Not very close to each other, which means we detect only one electron in whole piece, not broken. So at a time, when we are plotting this, basically if we talk about this position, let's say, this position, at this position, we detected only one electron at a time. So click, 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 and that way we plotted this. Okay? Number of counts. Obviously, the other hole should not have any effect on electron passing through this hole. I mean, if the electron came through this hole, then it came through this hole. The other hole should not have any effect on it. It's like saying, whether I keep this hole open, hole number 2, or not, doesn't matter. It should not matter. Because the electron it's a lump. It's like a particle, we assume. So if it hit the detector, if it hits the detector, it came through one of the holes, not through both. Came through either this or through this. And then, and that means our final probability should be just the sum of P1 plus P2. Independent probabilities just sum up. We should see a bullet-like behavior. A sum of these two should be our P1 to when we closed, when we kept the both holes open. Instead, what we see is a wave-like pattern. When we had waves, we had seen intensities behaving strangely like this because of an interference between the two holes. But where is this interference coming from? I mean, imagine one electron coming and passing. The other one will come later. How can that interfere with something in the future? This electron that got detected by this detector is already detected, means it came, it passed through either this, let's say this, and then it's detected. After some time, another electron might come, and that might go through another hole, but it cannot affect the past, right? That's in the past. That electron has already passed through the hole. There cannot be any interference. Can it be? Can there be any interference? I mean, we can again imagine like two electrons coming together. Then yes, one might interfere with the other. But at a time only one electron is going. It doesn't know that if it's passing through one hole, it doesn't know that there is another hole through which another future electron might pass. It doesn't know. So we do not expect an interference. And only from interference we could see a pattern like this. So where is this interference coming from? Somebody might say that maybe, electrons have strange paths. Maybe one electron, although it's just one at a time, but this electron coming and going back through another hole, and then coming back through this hole and hitting the wall, right? Or just imagine that. So if that's what the case was, so electron coming through this hole, then doing some weird, U-turn and going through hole number 2 in backward direction, and then again going through this hole number 1 and reaching the wall. What would happen then if we closed hole number 2? If we closed hole number 2, then we blocked this electron. This would come and hit this our block, and then there wouldn't be this electron on the spot. But then that would mean there would be some gaps somewhere here. That electron didn't reach this position. There would be some gaps in some positions, or lower electron probabilities, right? When we closed one of the holes. But we see that when we closed one of the holes, we had nice and smooth probability distribution. Another point. So we would actually, if that was the case with both holes opened, and we see some really zero electron counts at this position, really zero, nothing here, a lot here, and zero here. Instead, when we closed, so what is this curve? P1 is when the hole number 2 was closed. So at this position, if you look, when we closed the hole number 2, we had more electrons here, not less. But we have just seen that if we had electrons behaving weirdly, like it passing through hole number 1, it coming back through hole number 2, and then returning through 1 again to reach the wall, and we blocked hole number 2, then we wouldn't get that electron in the detector. That means we would have lower number of electrons compared to, when both holes were open. But we see more actually. We see more. Closing 1 has more electrons compared to both open, where some positions are really 0. So this means that no, electrons are not behaving like this. Secondly, even this also gets contradicted. Look at this position. This is more than double. So if you added P1 here and P2 here, you would get a value like this, But this is more than even double the height, very high at this position. So at some positions, it's like closing, it's like at these positions, closing one hole lowered the number of electrons passing through the other hole. So at one point we have seen that it increases when we closed one hole, and in some position we see that when both holes are open we have more electrons. If we closed, we actually reduced the number of electrons passing through one hole. So the point is, with this complicated, like one electron passing through, taking weird paths, going through both holes like this and reaching the detector, is not able to explain. People thought about various possibilities like this, but they could not explain this graph, this probability distribution of these electrons when both holes are open. Well, one simple explanation can perfectly explain this distribution, and we know this. If we just imagined that when an electron gets detected, it certainly behaves like a lump, like it makes a sound click, like a bullet, but it has an associated wave with it. That associated wave that shows interference. So what I'm saying is, we are saying that an electron, otherwise when we detect, this is an assumption. We are trying to explain this behavior with some theories, right? So here, let's try to put a theory that simply explains this behavior. The theory is like this, like water waves. So what was water wave? If h1 was the height or amplitude of the wave, let's say h1 e to the power I omega t was the amplitude of wave coming out from hole number 1, and amplitude of waves coming through hole number 2 is h2 e to the power I omega t plus delta. Then intensity of this wave I1 would be equal to mod of h1 squared, and of course mod of e to the I omega t. means just one because it's purely imaginary. Well, e to the power I omega t times e to the minus I omega t. So if you take mod, that's 1. And intensity of this would be I2 equal to mod of H2 square. And what is the amplitude of the combined wave at any position? We know this. That is I12 equal to mod of H1 e to the power I omega t plus H2 e to the power I omega t plus delta mod square. If you do this, you'll see that it will be mod of H1 square plus mod of H2 square plus 2 mod H1 mod H2 cos of delta. That's our so mod of H1 square is I1, mod of H2 square is I2, and this is square root of I1 square root of I2 cos delta. So basically, let me write down in a simple way, is I1 plus I2 plus twice I1 I2 cos delta. This is the interference term. Similarly, if we considered that electrons are like this, electrons coming out of hole number 1 has a complex amplitude associated with it, which is given by, let's say, phi 1, and then electrons coming out of hole number 2 has another amplitude associated with it, so that the probability corresponding to this amplitude P1 is equal to mod of phi 1 squared, and probability of these electrons is given by mod of phi 2 squared. Phi 1 and phi 2 are complex numbers. Complex number. Then the combined amplitude P12 will be mod of phi 1 plus phi 2 whole square, and you will see that in these cases, if you have two complex numbers, phi 1 and phi 2, any complex number, you will always have, if you taken the mod of the sum square, you will see mod of phi 1 squared plus mod of phi 2 squared plus an interference term, interference, and that explains this behavior perfectly. It's such a simple mathematical model that explains this. But intuitively, we don't understand this. We don't know. I mean, electrons, obviously, we feel like electrons are like bullets. What is this? So this is the strangeness. And experimentally, not this exact experiment, but an experiment in principle is exactly like this. Not this exact setup, but in its spirit, a very similar experiment. Such experiments have been done repeatedly, and interference between electrons have been seen. Between, when I say between, I don't mean between this electron and then another electron. because we know that we are taking a very low rate of electron. So at a time only one electron is coming out, right? So it hits the wall. What we really see is this. So one electron is coming, click. Another one is here, click. Another one is coming, click. And we get some dots. What we see over time is that a lot of dots here at this position. And then less. And no dots here. Then some dots here. Then almost no dots here. Then a lot of dots here. Then no dots here, a lot of dots here. Then no dots here, then a lot of dots here. So if we plot this, they look like this. So what you see is this. And if you plotted the numbers, you see this. Function looks like this. Yeah. So the problem is that this is due to one electron coming at a time. One electron somehow knows that I have to go here. So most of the electrons will try to go here. Some of them will try to go here or here. None of the electrons want to come here. Okay, none of the electrons are coming here. None of the electrons are coming here. None of the electrons are coming here. None of them are coming here. They're choosing some position more. Somehow they're coming out, but they know, I want to go here more. I don't want to go here. I want to go here more. And over time, you get these dots accumulated more in this position, very less here, more in this position, and like that. So when you plot it after extended period of time, in 1 hour, let's say, you would start to see a pattern like this. And that's very weird, very strange. That can only be explained by considering that when electron gets detected, it's definitely like a bullet, because we see a dot for sure, a dot, not some spread out. Click, and there is a dot. If you have a photo film, you'll see a dot. Okay, then after some time there is another dot. So let's really do it. Okay, let's really do it. What we are going to see is something like this. We get it? Tick, a click dot. Then sometimes there's a click dot. Then after some time another here. Then one 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 here. 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 So when you wait for an hour or so, you start to see pattern like this. There are blanks, no dots, no clicks here, no clicks here, more clicks here. So when you plot it, you see brightness, darkness, just like interference patterns of waves. So if you plot it, you see this. And this clearly could be explained by a simplest model if we just imagined that an electron has an associated complex amplitude like waves. And in that sense, we say that electron, being a particle, sometimes behaves like a wave. I would I would like to rephrase that, and I would say that an electron probably is neither wave nor a particle, because particles and waves are properties that are classical, that are coming from our classical understanding, our intuitions. Like, we see bullets, we see balls, we see stones, and from those we create this idea of particles. We see water waves, we see waves on strings, and we build the idea of waves. So waves and particles are really absolutely our intuitive classical ideas of this world that surrounds us. So a particle is an object of the world that we experience, okay? And waves are also objects of this world that we experience directly through our eyes or touch and so on, or hearing. But microscopic world, maybe these things don't exist. So electrons is something else entirely. But when we want to understand an object like this, a microscopic world, we try to see it through our, specs of classical understanding. And that's why we try to see it as either waves or particles. And that's why we push these ideas onto the electron. But maybe electron is neither particle nor wave. So we say that we see sometimes it behaves like waves and sometimes it behaves like particles. And that's it. So with this, we close the introduction of the strangeness or weirdness of quantum mechanics. We will proceed to more formal introduction and mathematical or postulates and all these things. But before that, I just would like to tell you that if you find this very strange, very weird, that you don't understand, then you are not alone. In fact, everyone feels that way. And even Richard Feynman, one of the pioneers of quantum mechanics and one of the founders of the quantum mechanics, not founders, but developers of quantum mechanics, and one of the founders of quantum field theory, the most successful theory in any branch of science. He himself said, it can be safely said that nobody understands quantum mechanics. So with that, I'm going to end this lecture and see you offline in the next lecture, but we'll try to record those lectures too for the students who are not able to attend us offline. Thank you.